For most people that build programs, computer code is expressed as a structured, high-level language generically referred to as software. The foundation for this is low-level machine code that operates the native instructions of the CPU being used. In modern computers, this can be picked apart even further with microcode that describes partial instruction steps that, when composed, form those machine code operations. All of this requires dedicated silicon that is physically defined in how the circuits and gates are etched. CPLDs and FPGAs are born different. They still have physically etched circuits and gates, but these are designed as grids of gates controlled by a form of persistent memory. Changing the value of the memory changes not only how the gates behave, but how they are joined together. This allows the developer to create synthetic hardware. For an example, you can program the memory to let the host chip behave as a recognized CPU, plug it into an existing computer, and have it operate exactly as the original. The standard for programming these chameleons of the digital world is hardware definition languages, from CUPFL to VHDL to Verilog. CUPFL was created to unify the design of different PLDs, but becomes hard to work with as the design scales. Ironically, VHDL was not created to design logic. It was intended to document digital hardware, but has become foundational to define how the more complex PLDs work. As a result, VHDL is a de facto standard, but comes with a bunch of limitations. Verilog, or System Verilog, has a different set of problems, but is, if you listen to manufacturers, the preferred approach. Other options exist, typically centered around graphical design interfaces that allow the developer to create systems in much the same way as creating physical PCBs. No one solution wins, unfortunately. My choice is typically to use Verilog, as it allows for great control when designing virtual test benches to verify what you've coded actually behaves as intended. And this is also one of the problems with Verilog. You can design and test stuff that can't be synthesized. The first bit of the design I'm going to dive into is the VDG, where I started on this project. Externally defined by a data bus, address bus, a clock, some control signal inputs, 4 control outputs, and 4 analog video output signals. For my purposes, I'm only interested in the very least bit of the address bus, so the remaining address pins are ignored. For the data bus, in the real world, it is latched and buffered externally to provide signal stability, but that can be brought inside the design, although that in turn may trigger, but we already have a suitable pin in the form of MS. In the Dragon Coco use case, 2 of the control signal pins are tied to the data bus. Those 2 can be brought inside the design as well. The analog output, as previously discussed, is a headache. PLDs don't generally do analog signals. They can through PWN, but that tends to be problematic for video. My solution is just to output digital RGB and deal with digital to analog conversion externally. This decision means I can't just plug my design directly into a socket where the original 6847 VDG lives, or lived. On top of this, there are 2 more outputs for vertical and horizontal sync and a row reset pulse for an external character ROM. I need to keep the sync signals, but I don't need the reset pulse. One extra detail is that I want to be able to switch between NTSC and PAL frame timing, so I need an additional signal on input to control which is in use. The tally then is that I lose 11 out of 12 address pins and 3 of the 10 control signals. On the other hand, I add in the output format, and instead of just 4 pins for video, I have 12. The final score then is, instead of 38 pins on the original chip, I only need 32 pins in my implementation. Enough hardware, I promised implementation details. Internally, the VDG has to keep track of horizontal and vertical positions to drive the frame timing and which bit or bits of data are actually being displayed. The position and data combined with control signals define the color of the output and how often the signal address bit changes. If you want to see a deep dive on how to create a TV signal frame, I really recommend watching Dr. Matt Regan's videos on the subject. He uses state machines to do the job, but in HDL, this doesn't work so well when the geometry is variable. I use dedicated functional block that counts rows and columns of pixels to switch internal controls on and off. The input is just the clock, mode and format. Sounds simple, but this is honestly the most complicated part of the classic 6847 implementation. It is still a state machine of sorts, but it has its fingers in a lot of pies, governing display state, sync, backport, border or viewport, the speed of the pixel clock, the address clock, and the row counter for text modes. Deciding which bit of the input data is being displayed is traditionally handled by shift registers. Load the input data on a clock transition and then shift bits out as needed. If the 6847 was only a single bit per pixel, this would be the easy option, but that isn't the case. There are modes where 2 bits are needed, and when talking about semi-graphics, the relevant bits depend on the row, not just the horizontal position. Instead of a shift register, I have some specialized logic clauses that pick out the needed bits depending on, you've guessed it, horizontal and vertical position. I already have a set of these and then use the display mode controls to multiplex them into a single output. I also need to select color. The 6847 is more than a little odd in that it generates 12 different colors. Things get trickier in that there are 4 more colors generated in NTSC due to video artifacts. Those video artifacts only work in one specific mode, depend on which clock phase the color carrier signal is using when the color burst is generated, and you can only get 2 of them without doing some electrical gymnastics. To select the right color for the displayed pixel, I use the same multiplexing trick to choose between the possible palette options. Thankfully, the first 8 colors are consistently numbered, but then you have black. Actually, there are 3 different blacks, and they are all indicated as the absence of a color rather than being a color. I've said it before, and no doubt I will say it again. The 6847 has some interesting behaviors and limitations. The final ingredient in all of this is the character generator. The original 6847 has a set of 64 5x7 pixel glyphs that are hard etched into the silicon. A single character on screen occupies an 8x12 pixel block, which immediately highlights a bit of a problem. The character generator has to fill in the gaps and optionally invert the pixels depending on the state of the inverse input. When I first coded this, I naively generated a conditional table that returned the relevant 5-bit pattern depending on the row and character data. It turns out that this is actually a bit of an issue. The 64 by 5 by 7 table needed to contain the bit patterns is not large, but constitutes a big chunk of the programmable resources in the CPLD. FPGAs actually have dedicated memory blocks for this sort of thing. So remember when I said I don't need that reset pulse? It turns out I was lying to myself. What I actually need is a row counter and an external character ROM. It also means that I need another set of data bits. I could wire the data through the same bus and switch sources externally, but one of the things CPLDs are good for is lots of I/O pins. The external character ROM has the address bits driven by the row counter and the same data bus used for regular data input on the CPLD. The data output from the ROM goes to a dedicated set of 8 data inputs. The result is I just need to select which data bus to input from. Amazingly, this is almost the entire design, but there is one more signal I need to worry about. That single address bit output. This connects to the SAM and drives the video address register, effectively an additional clock. The address bit, DA0, changes whenever the VDG needs a new byte of data. The SAM advances the video address and, in the video slice of the clock cycle, presents the new data to the VDG. Superficially, this is simple enough, but it comes with a nasty gotcha. DA0 can only change in a limited window within the master clock cycle. If it changes outside of that window, the SAM pulls the rug out and suspends the video clock until the change would be in phase. The problem is that the VDG has no idea whether it is in phase or not, but it absolutely must maintain the phase once established. Any mistakes result in the video clock vanishing, and this in turn causes the synchronization of the video output to be disrupted. In the real world, this appears as a flickering top left corner of the screen that wobbles around. An additional side effect is that in NTSC, you lose the colour from the display. Keeping the phase correct within a single frame should be simple enough, but DA0 is not clocked all of the time. It pauses for the border area and needs to be cleared on vertical sync. The problem is that it has to be cleared exactly the right tick within the vertical sync, and this has caused me no end of grief. The amazing part of all this is that the entire design fits inside a very modest CPLD. I did all of the original development using Altera Max 7128. This has just 128 macrocells, the currency of PLD resource. With further optimization, it might even fit in a smaller device, which means it is only slightly more complex than the really early programmable logic devices of the early 80s. The problem with those devices is limited I/O, however, so there is practically no reason to optimize down. The real issue here is that those CPLDs are out of production. Atmel make a plug-in replacement, but even that is end of life. The next realistic option is the Max 2. This comes with substantially more internal resources, which then begs the question, what am I going to do with it all? That, however, will wait for another update.